Hi everyone. Today we're going to talk about molecular compounds. So we are done with ionic compounds. We finished those last week and hopefully you tried the quiz. If you haven't, stop now and go do that first. But if you have done that, then we're going to move forward with molecular compounds. You may also hear these, like if you're Googling stuff or if you're looking things up, as covalent compounds. Just a different name for it, but for me going forward, I'm going to be using the term molecular compounds, but just so you know, so you don't get confused, they are also called covalent compounds. Okay, so hopefully you have either, the note that I put on Google Classroom or your own sheet in front of you, and um, and hopefully you tried the matching sheet as well. If you haven't done that, maybe pause and do that first, just to start to get an idea. I bet you guys probably figured some of the rules out, but if not, that's okay. Here we go. Okay, what is a molecular compound? So a molecular compound is formed between a nonmetal and a nonmetal, so two anions coming together. And the bond, remember that bond means what is actually holding these atoms together. This bond is formed by sharing electrons. And the overall charge of a molecular compound is not always neutral. So ionic compounds, when we transferred electrons, we would end up with a neutral charge. Not always the case with molecular compounds. So if we pause here and just kind of compare the two, what we know about the two types of compounds so far, if we have an ionic compound, we know that we're looking at a metal and a nonmetal coming together, whereas a molecular compound are two nonmetals. If we look at the type of ions, we've got a cation and an anion coming together in an ionic compound, and in molecular, it's two anions. And if we're looking at how the electrons move, or what's happening with the electrons, in ionic compounds, there's a transfer going on. And remember, we showed that in our Lewis diagrams with a little arrow. We showed that one element is going to be transferring its electrons to another. Whereas in molecular compounds, they're going to share. So they're going to come together and they're going to share those electrons. Some properties of molecular compounds include they're usually soft and flexible. They usually have low melting and boiling points, and they are not typically electrolytes. So they're not going to be able to be put in solution and conduct electricity. And a fun fact is that most compounds on Earth are molecular compounds, particularly anything biology related. So plants, animals, us, we're made up of mostly molecular compounds. Okay, so how do we show a molecular compound? So we're going to go through the diagrams, the Lewis diagrams for a couple of these just to kind of get the hang of it. So if we have carbon and oxygen to start with, let's show the Lewis diagram of both carbon and oxygen. So if we start with oxygen, again, we know that's in group 16, so it has 6 valence electrons drawn around it. Carbon is in group 14, which we haven't really talked that much about so far, and carbon is able to form molecular compounds, not really ionic compounds. So carbon is in group 14 and has 4 valence electrons. So instead of there being any sort of transferring going on, we're going to start to share electrons. And we show that by drawing a circle around a pair of electrons that will be shared. So right now, if there's a circle here, that means these electrons kind of split their time between oxygen and carbon. They go back and forth, but they kind of belong to both now. So oxygen now has 1, 2, 3, 4, 5, 6, 7 electrons, and carbon has 5. So we're close. Oxygen's almost happy. We want 8. Remember, we want that full valence shell. So we can share another pair. And so again, go around and count 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 electrons around oxygen. Oxygen is happy. Carbon, on the other hand, has only 6. We've got these 2 on their own here. So we might need to add in another oxygen and create 2 more bonds. So now you should be able to go around and count and make sure that all of our, or each of our elements here has 8 electrons. And they can count for both. So when I went around and counted that this first oxygen has 8 electrons, when I go to carbon, I still count those again because they're being shared between the two. So if we count carbon right now, I've got 1, 2, 3, 4, 5, 6, 7, and 8. And we should find that the same thing goes for our last oxygen there. So we've created 4 bonds in total, and that's shown by those rings around the electrons. And so that is our finished molecule. So that's the Lewis diagram, and you can see that it's a little bit confusing, it's a little bit messy. So there's something new that I'm going to show you called a structural diagram, and that's used for molecular compounds just to kind of clean things up a little bit, to make it look just to make it look a little bit more simple. So, and basically the only difference between a Lewis diagram and a structural diagram is that we're going to represent this bond, this sharing of electrons, with a straight line. So that looks like this. So we've got our oxygen, still the 2 pairs of free electrons there, but then we're going to show that we have 2 bonds between that oxygen and that carbon, and 2 bonds with the second oxygen as well. And so you just have to remember, if you're looking at a structural diagram, that each line represents 2 electrons. So if I were to try to count to make sure that I have enough electrons or the right amount of bonds on my oxygen right now, I could look and see that I've got 1, 2, 3, 4. This line represents 5, 6, and this line represents 7, 8. So we're good. Oxygen has a full 8, and you can do the same counting for the other 2. So our chemical formulas and names are pretty much the same. We're using subscripts, the little numbers, to show how many of each element we have. So the chemical formula for this would be CO2. That's a subscript there, that little number. And the name of this is carbon dioxide. Okay. Let's look at fluorine and fluorine. So molecular compounds can sometimes see an element bonding to itself. That's actually really common. So if we look at the Lewis diagram for that, fluorine is in group 17, meaning that it has 7 valence electrons. So it looks like that. And we're going to bond to another fluorine. So this one's actually nice and easy. They both just need 1 more electron. So they can share that unpaired electron in the middle, so that becomes 8 for each of them. So again, you can go around and count and double check, but we should find that each fluorine now has 8 full valence shells. Sorry, full valence shell, 8 electrons. There we go. Okay, so and then the structural diagram, pretty much the same thing. We're just going to represent this bond with a straight line. So it looks like that. The chemical formula for this is F2, and whenever we have a element bonded to itself, we call that a gas. So this is fluorine gas, and if ever you're going backwards, if you're given the name and you have to draw it, if you see fluorine gas or oxygen gas or nitrogen gas, that means that you have that element bonded to itself. Okay, let's try a little bit of a trickier one. So we've got phosphorus and sulfur. So I'm going to start with sulfur here. It's in group 16, so it has 6 valence electrons. So I've drawn that there. And then we've got phosphorus in group 15 that has 5 valence electrons. So we're going to start to draw our bonds in. We know that we want to share some of these electrons. So if we share those 2, then we can go around and see that 1, 2, 3, 4, 5, 6, 7, 8. Sulfur is happy. Phosphorus is not quite there yet. We've got one empty one here. So we're going to need to add in another sulfur. And then we can bond that. So now that phosphorus is happy, we can go around and count 1, 2, 3, 4, 5, 6, 7, 8. So that phosphorus is happy. However, now this sulfur, this new sulfur, is not happy. So it's kind of like before when we were doing our ionic compounds. It's a little bit of trial and error. You kind of need to keep adding things until you get it to all to fit together, because we're trying to make a neutral molecular compound here. So let's add in another phosphorus. We can draw in another bond. Almost there. Phosphorus isn't quite happy. Let's add one more sulfur. And there we go. So if you're double checking your answer, you kind of want to look around, make sure that there's not one electron all by itself, that everything has been bonded that is sharing with another element here, and that each element, if you were to count up the electrons, has 8 around it. So the structural diagram for this, to kind of clean it up, because again, especially once we start to get a lot of elements involved, it gets really messy. So to use the structural diagram to show this, it would look like this. So we've got 2 bonds here between sulfur and our first phosphorus. So we've got 2 lines there. We've got 1 bond between phosphorus and the second sulfur, and then in between here, and then 2 bonds at the end. So you should be able to go through, just like you did on your Lewis diagram, on your structural diagram, and count the electrons and make sure that each has 8 around it. So this one, the chemical formula for it, is P2S3. We've got 2 phosphorus there and 3 sulfur. And the name of this is diphosphorus trisulfide. So by now, you're probably recognizing that there's something going on with the naming of these. There's something that we haven't seen before, and you may have picked up on it in the matching sheet. If you haven't, that's okay. Let's figure out what that means. So when we're naming molecular compounds, first of all, the names of the elements should be in the same order as the chemical formula. So, and as a rule of thumb, the element with the smaller group number always goes first. So let's pop back for a second and just look at this one. So first of all, if you're given a formula, P2S3, the name would be diphosphorus trisulfide, not trisulfide diphosphorus. You're not going to switch those. You want to keep the same order. And the reason that I put them in this order is because phosphorus is in group 15, sulfur is in group 16. So the one with the smaller group number, it goes first. That's the rule of thumb. Okay, so that's kind of our first rule. The second rule is that the ending of the second element gets changed to "ide." So this is the same as ionic compounds. We're used to this. We always are going to change the ending of the second element to "ide." And then the biggest difference, and what you've probably noticed or hopefully noticed so far, is that we're adding these weird prefixes to indicate the subscript numbers. And so those prefixes are right here in the chart. So if there's only 1, you say mono. If there's 2 of something, you say di, 3, tri, 4, tetra, 5, penta, 6, hexa, and it goes on and on. So again, if we go back quickly, you'll see that we had the subscript on phosphorus is a 2, so we wrote diphosphorus. If or our subscript here on sulfur is 3, so that is trisulfide. So we always are going to add those prefixes to both names in a molecular compound. And again, you don't have to memorize these. They are found on that same chart on the back of your periodic table on the right here. So you can always reference that whenever you're working on practice questions or doing a quiz or anything. Those are always there for you. There's an exception, always an exception to the rule. And that exception is that you're never going to add mono to the beginning of the first element. So, and that's just, It's the weird one. You're going to add mono to the second element, but not to the first. So if you have a chemical formula where you only have one of your first element, you're not going to add mono. You just say the name of the compound. So let's go through some examples to hopefully make a little bit more sense. Okay, so our first one is exactly that. So we've got only one carbon because there's nothing written here. So we've got one carbon and then two oxygen. One is normally mono, but because it's our first element, we don't write it in. That's the exception. So this just ends up being carbon dioxide. If we look at the second one, we've got one of each. So we don't add mono to the first one, but we do add it to the second one. So this is carbon monoxide. Our third one, same thing. We've got only one here and then three chlorines. So this is nitrogen trichloride. And then, if we have any other number than one, if we have, 2, 3, 4, 5 and above, we do have to write the prefix. So this one becomes diphosphorus tetroxide. It's a bit of a mouthful. So, okay, so hopefully that clicks a little bit. Any other number than one, we do write the prefix on the first word. If it's a one, we don't write mono. Let's go backwards. So if you have the name and you're trying to come up with a chemical formula, this is actually super easy. It doesn't require any crisscrossing at all. All you have to do is look for the prefixes, and that tells you what number to write. So if we don't see anything, that means there's a mono there, but obviously they haven't written it because they followed the rules. So we've got one sulfur and 6 fluorines. So that would end up being SF6. Iodine gas. Think back to our previous examples. If we've got something and gas written there, it means it's bonded to itself. So we've got 2 iodine elements. And then we've got dicarbon tetrabromide. So di, if you look on your chart, means 2. Tetra means 4. So that would be C2Br4. So that is everything, guys. I'm going to give you some practice to hopefully, get a little bit more comfortable with this. As always, if you have any questions about this, please email me or let me know if you want to do a Google Meet. But I hope that made sense, and have a great day, guys.